This is your presenter Asloob Mudassar, and I am presenting slide number 124 of the course on laser physics. Question is, the output intensity from a laser system operating either in a single mode or multi-mode can fluctuate with time, which is highly undesirable. Describe how can the intensity be maintained and what unit is used to specify the intensity noise fluctuations. The answer is amplitude fluctuation or intensity noise in an output laser beam depends on many factors. Some of the main factors are specified as given. Vibration of mirrors or vibration of cavity components, cavity misalignments, fluctuations in pumping source, for example, power supply current fluctuations or voltage fluctuations leading to instability in discharge, fluctuations in spontaneous emission process, and electron hole recombination noise as in a semiconductor laser, appearance of bubbles in the dye jet solution in a dye laser cell, etc., etc. These are the perturbations on fast time scale or the short-term fluctuations. Long-term perturbations appear when a laser system has a few thousand hours operation. The long-term perturbation involves degradation of optical components within a resonator, including mirrors, windows, active medium, etc., etc. The term used for noise representation is RIN, which stands for relative intensity noise. It is defined by RIN as a function of omega is equal to the integral from minus infinity to plus infinity, and the integrand is a function CPP as a function of tau multiplied by e to the power iota omega tau, and the integration is with respect to d tau. So this function RIN, which is called the RIN function as a function of omega, is used to represent the noise from an output laser beam. That is a noise in the intensity of an output laser beam, where CPP of tau is the intensity autocorrelation function defined by CPP of tau, that is CPP as a function of tau is equal to average of the autocorrelation function, that is delta P of t multiplied by delta P of t plus tau, and we have normalized it with square of the average power. You may say that this is the autocorrelation function, that is, it is an intensity autocorrelation function, or equivalently you can also say that it is a power autocorrelation function because it contains implicit information about the area. So area has not been specified, but implicitly you can say that the area is present in this expression. So if not, then you can call it as a power autocorrelation function. So PP as a function of tau is equal to the average value of the autocorrelation function of the power output divided by the square of the average power, where this sign, that is the average P, is the average output power, and delta P of T is the fluctuation in output power around the average value. For a single mode laser, the dimensionless quantity to specify the intensity noise is sometimes defined as. So you see that here we are talking about single mode laser. not multimode. For a single mode laser, the dimensionless quantity to specify the intensity noise is sometimes defined as. So this is specific to a single mode laser. That is equation number 3 is specific to a single mode laser. And the RIN function has a unit of decibels and hertz. Don't say that hertz is dividing the decibel. So you can say it is comma or just a separation. So RIN as a function of decibels and hertz is equal to 10 log of RIN as a function of nu multiplied by delta nu. We can also express this one in terms of omega and delta omega, but here we are going to express it in terms of a single laser frequency because we have a single mode operation. So this mode is represented by the frequency nu. So nu stands for a single longitudinal mode. So we have RIN function defined as for a single mode laser is equal to 10 into log of RIN of nu multiplied by delta nu, where RIN of nu is equal to 2 pi RIN of omega. So this, you see that this is the relationship between the RIN of nu and the RIN of omega. And the noise is measured in bandwidth of 1 hertz, that is delta nu is equal to 1 hertz. So you see that when we want to measure the noise for a single mode laser, that is when we want to measure this quantity, we have to measure that quantity in a bandwidth of 1 hertz. Sometimes the relative fluctuations of the output power, which may be represented by the ratio of delta P of t divided by the average power, or the root mean square variation of delta of P of t. The root mean square variation, which is represented by the square root of average of the square of delta P square of t is divided by the square of the average power. So this represents, you see that the root mean square variation of delta of P of t. So sometimes this quantity, that is the delta P of t divided by the average power, is of interest, which represents the relative fluctuations in output power, or sometimes the root mean square variation of a fluctuation in power is of interest, and this is represented by this function. To stabilize intensity output from a laser, or equivalently to reduce the intensity noise, a negative feedback system, or to reduce the feedback noise, a negative feedback system is applied, which means that you take a sample, that is you take a sample of the output laser beam and use it as a feedback mechanism. So a feedback system is applied which gives a feedback signal to the pumping mechanism. So you take an output from the laser source and then you give a feedback signal in the form of an electronic signal, that is the optical signal from the laser source will be converted into an electrical signal, and a negative feedback is then given to the pumping mechanism. The response of the feedback system must be lower than the pump rate response time. So you see that this is the condition, that is the response of the feedback system must be lower than the pump rate response time, so that the pump rate can accommodate the feedback system response and then can implement it. Because if the feedback system response is faster, the pump rate would not be able to accommodate that change. Diode laser as the pump source, which may be used as a pump source for a solid state laser system, has a response time much shorter than the inverse of the relaxation oscillation frequency. So you see that what is the meaning of relaxation oscillation frequency? When a laser is switched on, in the beginning the laser is highly unstable. That is, the amplitude of the output laser beam is highly unstable. and after some times it takes some times to stabilize. That is called the relaxation oscillation time, or equivalently in terms of a frequency it is called the relaxation oscillation frequency. So after the relaxation oscillation time, the laser intensity is somewhat stable. So you see that here we say that the diode laser as a pump source for a solid state laser has a response time much shorter than the inverse of the you can say than the relaxation time, or you can say that than the inverse of the relaxation oscillation frequency of the solid state laser. That is the response time. That is, the diode laser has a pump source which is used to pump the diode, which is used to pump the solid state laser, has a response time much shorter than the relaxation oscillation response time of the solid state laser. The feedback response time could be as large as that of the relaxation oscillation time, or as that of the inverse of the relaxation oscillation frequency. For multi-mode lasers, the intensity stabilization. Now you see that we are talking particular, this paragraph is about is about multi-mode laser. That is a laser that is a laser which has an output containing a large number of a large number of frequencies, or a large number of longitudinal modes. For multi-mode lasers, the intensity stabilization is much more difficult with a feedback system. If a feedback system ensures a constant output power, which is of course the purpose of a feedback system, to ensure a constant output laser power, the power corresponding to the individual modes will fluctuate with time. So you see that now the output power, which contains many output laser frequencies, if you measure the output power of such a laser averaged over many frequencies, then of course the power stays constant. But the power corresponding to the individual modes or to the individual frequencies lasing out with the laser will fluctuate with time. That is, you cannot control the power of the individual longitudinal modes. That is, the power of the individual modes varies in a non-linear way, but and cannot be controlled, and we cannot assure the constant power for each individual mode. But under the feedback, the total output power stays constant. So you see that this is what we have said in a few paragraphs about the stabilization of the output intensity when it is operating in a single mode or in a multi-mode. And we have discussed how the power of such a laser can be made to stay constant. And this is the end of slide number 124.